Hello guys, welcome to my channel once again. Now we are going to discuss a topic called burning process in combustion chambers. Here we can see a schematic diagram of how the combustion process will be taking place from starting of injection to the delivery of uniform gas flows to the turbine. Here we can see a zone where we are going to inject fuel into the compressed air which is coming from compressor, and then it will get evaporated in this particular zone. And here in flame front, here the process of burning will start, and then it will get moved towards the mixing of secondary air, where there will be formation of circulations in this particular zone. Because of the movement of this secondary air, whatever the leftover particles of fuels will be there, they will be getting mixed with these secondary air, and then they will burn completely, and finally these gases will be delivered to the turbine. Next, limitings of this flame speed. The speed of propagation of a flame through a mixture of hydrocarbon fuel and air is rather low. The flame speed will vary with mixture strength, temperature, and pressure. For laminar flow of air, it is around 2 to 4 meters per second, but the average air velocity through a typical combustion chamber is around 30 to 50 meters per second. Thus, a region with low average local axial velocities must be provided if the flame is to be stabilized, sustained, and contained in one place. So here we can see a schematic diagram of schematic chart of flame speed versus fuel air ratio. Here fuel air ratio can be represented by F by A. Here we can see two regions. One is turbulent region, second one is laminar region. In this laminar region, burning rate will be low, and whereas in turbulent, burning rate will be of high. In this psychometric combustion process will be seen in this particular zone, that is in the range of fuel air ratio of 0.0502 to 0.075. Next, the flame speed is higher for turbulent flows and much lower for laminar flows. In laminar flows, maximum flame speed occurs at lower fuel air mixtures with stoichiometric mixture limits. Stable burning of hydrocarbon fuels takes place close on either side of psychometric values of fuel air ratio. It is necessary to ensure that the mixture strength is in the sheltered region is close to this psychometric values. The range of stable operation vary with the total pressure in the combustion chamber, which decreases with increasing altitude till cruise flight is reached. In defining stability limits defined in terms called equivalent ratio, that is represented by pi cc, defined as it is used. So pi cc can be given as F by A, that is fuel to air mixture ratio, operation conditions to fuel to air mixture ratio, psychometric conditions. Here you can see different types of fuels, that is basic aviation kerosene, JP4, ZB, JP5, and ZA commercial. These are the types of fuels which we will be using in aviation. Basic aviation kerosene can be used in commercial aircrafts, whereas JP4 or Jet B can be used in military aircrafts. JP5 is for safe fuel conditions, and JPA for commercial. So here we can see hydrogen or carbon property. Hydrogen by carbon property of a basic aviation fuel is 1.93. Similarly, if you see with military aircraft, that is 2.02, and ZP5 will be giving you will be having 1.92, and similarly Jet A commercial will be having 1.94. So if we go with initial boiling point, end point temperature, flash point temperature, freezing point temperature, these will vary according to the uh, purpose and according to the aviation type which we are going to use. Similarly, we will be having heating value, density, specific gravity, psychometric air to fuel mixture ratio can be seen over here for different fuels. With this, we will be winding up the video. Thank you for viewing. If you like the video, please do like, share, and subscribe.